All right, so welcome everyone to this webinar about integrating quantum computers into HPC centers. My name is Yuval. I'm Chief Marketing Officer of QuEra, and we have a very distinguished group of presenters today. Dr. Bob Sorensen, Chief Quantum Analyst for Hyperion Research. Bob, thank you so much for joining us.
Thank you. Glad to be here, Yuval.
And who are you and what do you do?
So as it says there, Chief Quantum Analyst for Hyperion Research. And I don't want to spend too much time on intros, but just to give you a background of Hyperion, we are an HPC advanced computing company. We do consulting for HPC suppliers and HPC end users, which means that we are not a quantum specific company. We look at the entire spectrum of advanced computing. When big data came along, we tracked what was going on there. When GPUs came along, we looked at GPUs' contributions to scientific computing, and then what happened in terms of artificial intelligence, all the way up to large language models, which are demanding entirely new architectures. So in some sense, we look at quantum computing as yet another tool in the toolbox for advanced complex workloads and advanced computing requirements. And so that's kind of a unique perspective, but it's also why I was so interested in this particular webinar today, because this is not looking at quantum as an island. This is about looking at quantum computing as it exists, integrated into an existing or new computational environment that has a wide range of complex and vexing computational requirements, and they're just trying to get their work done. And if quantum can do that, fine. If GPUs could do that, fine. But these users are always looking for the next best thing, always looking for the next new computational driver that allows them to kick the can down the road on their most compelling compute requirements.
Perfect. Thank you, Bob. And I always learn something when I listen to you, and looking forward to learning some more things today. And my other colleague, Dr. Tommaso Macrì. Tommaso, welcome. Who are you and what do you do?
Welcome, everyone. Thank you, Yuval, my colleague at QuEra, and I'm a senior research scientist here at QuEra Computing. Since I joined QuEra, I've been working on applications development as well as client relations, and more in particular with HPC centers. I'm very happy that Bob Sorensen is joining us today. So welcome, Bob.
Thank you.
And of course, I would like to welcome all our attendees. If you guys have any questions, we would be very happy to answer them. And please feel free to connect with us after the end of the webinar. And here's Yuval.
Excellent, thank you. And we're going to try to limit the number of slides. So I'll give a very, very quick intro about QuEra, and then pass it to Bob to present a few slides from some of his research. And then Tommaso will present, in short, our product line and what you can do with our applications. But then we'll have a discussion both between us and hopefully with questions from the audience as well. So QuEra is based in Boston. We build quantum computers based on neutral atom technology. Our 256 qubit machine is publicly accessible since November of last year on Amazon Bracket. It is the largest publicly accessible computer in the world measured by number of qubits. This is so important, I'm actually going to say it again. Our 256 qubit machine is publicly accessible live on Amazon Bracket since November of last year. Anyone in the world can use it as long as they have a Bracket account. And what we've seen is beyond enthusiasts and students and so on, that dozens of organizations regularly use this computer to submit jobs again and again. And in fact, the demand has been so encouraging that we're looking to increase the number of hours very soon that it's available online. Our focus as a strategy for the company has always been of delivering real-life value at every stage. And what that means is we're not just saying, come back in 5 years and we'll have a really good quantum computer for you. We're saying we have a good quantum computer today, we'll have a better one next year, we'll have a better one the year after, but hopefully at every given stage, you can do something useful with it. And we believe, perhaps a topic for a different conversation, we believe we have the key ingredients in place for the holy grail of quantum computing, which is large-scale error-corrected device. Not today, in the future, but we're well on our way to achieving that goal. Bob, would you like to present a few slides, please?
Yeah, sure. Thanks. Let's see if I can maintain credibility here by sharing my slides quickly. There we go. So this is just our cover. I already gave a quick overview of what we are here at Hyperion. You know, the key is it's all about advanced computing. It's not about quantum. It's viewing quantum as yet another tool in the toolbox. So I just want to run through a couple of things just from a 50,000 meter perspective on what's going on in the quantum computing sector writ large. We do an annual study each year trying to figure out exactly where the quantum computing market from a global perspective is going. And we do this for a number of reasons. We want to make sure that the suppliers understand where growth opportunities are. The end users understand that there is some stability here, that there is a growing market. It's not a hockey stick just yet, but there's some stable, steady growth here. We want to make sure that policymakers knows that some of the investments that they're making in terms of funding projects, supporting particular companies, export controls, supply chain concerns, whatever, is not sufficiently impacting the growth of the sector either positively or negatively in unpredictable or uneven ways. Uneven by in terms of national policy, say in the EU versus what's going on in the US or China or Asia Pacific countries. It's within Canada as well. So we do this study, and what we do is we go out and we want to make sure it's data driven. So using the letters of recommendation, if you will, from organizations like the Quantum Economic Development Consortium, the QuIC in Europe, or QSTAR in Japan, these kind of pre-competitive consortium organizations, they give us the credentials to say, go out and talk to quantum computing suppliers and ask them some questions that they normally wouldn't answer. But because this is for the good of the sector, we promise confidentiality, we present data in the aggregate, but it's important to get the data right. So we really go out and we hit a lot of different organizations. And this year, we finished the study in late 2022. We managed to get about 145 respondents from 18 different countries, representing 108 quantum computing suppliers. And we had very good success hitting all the ones that we really wanted to make sure we had an accurate understanding of. And by asking them things like revenue and growth and some of the technical details of their operation, we're able to really come up with what I consider to be a relatively credible estimate that the market is going to be worth about $770 million in 2023, with an annual growth rate of about 25%. And there's our three estimates that we've done in 2019, 2021, and 2022. And you can see we've had some pretty good success in really tracking what I call a market that's exhibiting some slow, not terribly slow, but the idea is stable growth going forward here. And to me, that's a pleasing concept. Well, let me just pull some other things that came out of that particular study. The quantum computing supplier base is very diverse. About 7% of the surveys, the firms that we surveyed, had revenues in quantum computing of more than $10 million last year. But what was interesting is about half of them had revenues of less than 500,000, and 32% have no quantum computing revenues. So we're still looking at a very bimodal kind of market here. Some very significant players with deep pockets, which in many cases are part of a larger state of product offerings, primarily in the classical IT sector, but also a lot of organizations that are still not revenue generating, are dependent on either government funding, corporate venturing, or venture capital, which again has some of its own advantages and disadvantages. One of the things we found when we asked about, and we'll get into some of these in more detail in a minute, basically about 70% of all quantum computing revenues in 2025, the suppliers expect that will somehow touch base with cloud service providers, the rest, of course, being the on-prem alternative. But really about 70% is envisioned for at least the next 2 to 3 years. Hardware revenues will compose about 35% of the overall sector revenues. Partnerships are pretty rife within the sector. About 75% of the firms we talk to do have some kind of partnerships. And the reasons for the partnerships were access to hardware in the quantum computing and software realm, but also access to markets, verticals, and classical IT expertise. It's one thing to build a quantum computer, as we'll find out today. It's another thing to integrate it into an existing classical computing environment. And so many of these startups, specifically, that don't have a lot of experience talking to key verticals or don't really yet have the expertise when it comes to integration into classical IT infrastructures, are looking for partnerships to help ease the way, to build relationships with end users that, as I said earlier, they're not looking to explore quantum computing for the sake of quantum. They're looking to explore quantum computing to accelerate their existing workloads and open avenues for new quantum computing applications that give them things like competitive advantage, return on investment, drive innovation, and accelerate their R&D capabilities. Public or private, about ownership right now is about 60-40 on the public side. The top quantum computing end user sectors that we found when we asked these organizations, where do you see your greatest opportunity? The financial sector, QC R&D, the sector still has to feed itself. So actually quantum computing companies are one of the major consumers of quantum computing technology, and cybersecurity. But as I'll show in a chart in a minute, broad applicability was envisioned across the 18 other sectors we gave them choices for. And you'll see how broad that was. But the bottom line there was at least one or more organizations that are a supplier said, this is our top priority vertical that we're going after. And so the broad applicability thing here is, I think, again, a really positive sign for the sector. This just gives you kind of we asked them about how you saw the major algorithms breaking out by revenue. And the big three continue to be the big three: mod sim, optimization, AI, either whether it be machine learning or deep learning. Cybersecurity started to move up. I think this is more about awareness of post-quantum encryption and some of the publicity about what's happening there, more than it is about looking at quantum computing as a way to either defend against quantum attacks or something else. But I think that's more of a mind share issue than it is a reality. Monte Carlo processes, because we've seen lots of work in demonstrated quantum random number generators coming to the fore, the fundamental basis of good Monte Carlo processors, that's come out there. This is the hardware access model that we talked a little bit about. We said, how do you see end users getting access to quantum computing? Half said capability on cloud. Another said, 1 out of 5 said, no, we're going to be thinking about on-prem. And then we have the hybrid at about 17%, the idea of having some kind of situation where at some point you may be accessing hybrid. You may be accessing quantum computing on the cloud because you want to explore different modalities, but you've got your home machine committed to perhaps a production workload or something. So it's an interesting mix. This is a fuller examination of, as I said earlier, the top 3 end user sectors. When we said to these organizations, pick the top 3, and as you can see here, we gave them an awful lot of choices, and an awful lot of choices were opted for. Speaks again to the broad applicability of the sector. We wanted to also capture a little bit of what's going on in the pull part of the equation. We have the push, we have what quantum computing suppliers are interested in. So we wanted to talk to quantum computing end users, and we really wanted to zero in on what we called early adopters. Who were the folks that had actually started to dip their toe in quantum computing? And when we did this study, we wanted to say, let's go out and talk to 300 different organizations that are end users. And the big question became, how many organizations are we going to have to talk to get 300 yeses to our first question, which is, do you have some activity in quantum computing? And we were all very surprised, somewhat pleasantly, that we only had to reach out to about 485 organizations, which means that 62%, about 2/3 of the companies we reached out to, and we had some other screening questions, which really were about annual revenues and significant IT budgets. I think the IT budget had to be more than, say, 10 million a year. We wanted companies that actually had the financial wherewithal to really think about quantum. So quantum is out there. End users are looking at it. They're kicking the tires. They're interested. There's different levels of activity. We found about 1/3 are exploring options and monitoring technologies. And that could be something as simple as having one of your new computational physics grad students looking at the technology 4 hours a week, all the way up to having some stand-up committed organizations looking at exploring the options. We saw a number of organizations, about a quarter, conducting use case analysis, and about 14% actually said production use. The things they're looking for, business efficiencies, but the greatest takeaway here is they're really looking for accelerating existing classical and adopting new quantum workloads. One of the interesting things is some of the greatest hurdles we found to QC adoption from these early adopters were complexities with integrating quantum computing into their existing infrastructure and clearly demonstrating quantum computing ROI. What we found really interesting was when we said, what was your vendor selection criteria? Sector-specific skills were up there, as well as the inverse of integration, the ability to integrate into the existing HPC center. Qubit modality and qubit specifications were actually deemed in low importance. I call this qubit modality fatigue at this point. A lot of end users hear lots of stories. There seems to be new modalities every day. They're more interested in use case demonstration. They're interested in performance acceleration on existing workloads. They are somewhat concerned about the ability for them to make judgments based on the deep technical merits of specific quantum computing architectures. And I think that's a cautionary tale for a lot of vendors in terms of you need to address the questions the end users are interested in, not the ones that help you differentiate your product among your competitors. It's really about end user visibility. It's not about my modality is better than his. But when we talked to these folks, we said, what's your attitude in terms of continued adoption? More than half are looking at measured growth, one-third see what they would call aggressive efforts, and only about 2% saw disillusionment. One of the things I did want to close, and this is my last slide here, is the idea of how does one talk to quantum computing end users? How do you find these early adopters? And who's driving early adoption within the corporate world? And what we found was, sure, the easy answer, CIOs, IT directors, they did dominate, but about half of the folks we talked to that self-identified as influencers within their organization to bring quantum computing into the fold, they're not C-suite denizens. They are programmers, hardware engineers, data scientists, subject matter experts, i.e. I am a chemist and I want to explore what's going on in quantum computing. And I go and call up my IT guy and say, I need access to quantum. What we found was most interesting is the quantum computing professional out there, not a lot of people have quantum in their names yet. The corporate tree, the chain of command trees, wiring diagrams haven't really addressed quantum computing as a subject yet. And so you just can't Google who does quantum at company X. You really have to dig down to find some of the key influencers. So I have tons more stuff if you're interested in any of this. I can send you more data, but that's really a fast and furious view of how we're looking at quantum from both the push and the pull sector.
That's very interesting, Bob. I'm curious about the HPC adoption. So when you speak with HPC center managers, where are they in the adoption curve? Are they saying, oh, we'll come back in 5 years and look at this? Are they starting to engage? Are they already engaged? Do they feel that they've missed the train? Where's the majority of HPC center managers in your opinion?
To be, HPC center guys, if you've been involved in the process long enough, you're always looking for the next big thing. The minute the new bright, shiny object comes along, you want it in your shop in 6 months. You want it in production in a year. And 6 months after that, you're looking for the next big thing. The classical world has experienced a bunch of end ofs, if you will, the end of Moore's Law, the end of Dennard scaling, the end of being able to pay for these things. To get a 10 to the 18 flop system, now you're looking at north of $500 million. Oh, and you're going to need 60 megawatts of power to do it, which means that if you own the machine for 5 years, you're dropping $300 million on electricity. So what's happening is a lot of HPC centers are figuring, what's the next trajectory? What's the next boost I'm going to be able to deliver increased performance capability to my end users? And so a lot of them are saying, is quantum the next big thing? Is quantum the next turn of the crank? The ones that, we've run GPUs for a number of years. We've gone through the pain and suffering of, say, converting legacy code to deal with this stuff. So again, they're looking at it more from what is the performance advantage that quantum can give me on my most important and compelling workloads? And that's the eternal question. It's always been the eternal question for HPC managers, and that's what they want to know. When can you deliver performance gains on the applications that matter to me? And it's if you can give them, and we actually did a study a while ago where we said, what kind of quantum computing performance gains would light up your life? And a very few people said things like quantum superiority, intractable on classical systems. And the numbers actually got pretty low, where people said, hey, if you can give us 20x performance or 30x performance boost on my existing application, I'm not too concerned about things like polynomial exponential speedups. I don't really give a lot of concern to the theoretical underpinnings. If you can give me 20x, that puts me 3 to 4 years ahead computationally of all of my non-quantum computing competitors. people will pay an awful lot of money today in the classical world for a 5x performance boost. So to me, that's really the metric that matters. It's the something X, the XX performance gains that really drive interest from the HPC center perspective.
Perfect. So we know that HPC center managers are curious about the next big thing, and many of them, fortunately, come to QuEra to talk about that. So maybe it's a good time to just talk a little bit about what is it that we are and what is it that we offer. So QuEra is a full stack company, which means we make hardware, software, and applications. And I think it's a good fit for this stage of the industry because everything sort of has to be tightly coupled to gain the maximum performance benefit. It's less likely that a single application is going to be entirely hardware agnostic and just run perfectly on every modality, regardless of the number of qubits and all the other parameters. So we're building flexible large-scale quantum hardware with unique features. We'll talk about that in a second. A development and emulation environment, which we call Blockade, which allows you to develop an algorithm to simulate it on a reasonable scale on your desktop and on a larger scale if it's installed on an HPC, the simulator, and then, of course, deploy and run it on the actual quantum computer. And then we have an applications team that is working with customers to develop unique algorithms for simulation, optimization, machine learning, really the big three that you mentioned. And Tommaso, maybe you could present a little bit of the product set that we have before we dive more into the HPC specific questions.
Absolutely. Thank you, Yuval. I already introduced at very high level the details of our company. What you see on the right slide, on the right of the slide is our main product, which is called Aquila. It's a 256 qubit machine that, as Yuval already mentioned, is available on Amazon Braket. It is a fully coherent machine for the whole duration of the computation. It is based on an analog mode today, but soon it will also be available on a more standard from the quantum computing perspective, gate-based mode. The other important technological feature is the so-called FPQA, or field programmable qubit array, in analogy to what is well known in microelectronics, the FPGA. So all these capabilities are actually very relevant to solve broad classes of problems. Yuval, if you can move to the next slide. Yuval already mentioned them at a very high level. So we focus, or actually the Aquila is able to solve problems that are in the domain of machine learning, and more specifically for classification and regression problems. And there are some native types of algorithm within quantum machine learning that can consist, for example, of the so-called reservoir computing that is very well fitted to the capabilities and the FPQA technology that we are currently implementing in our machine. The second set of problems, which are very important also for real-life applications, are optimization. One native type of optimization problem that Aquila can solve is the so-called maximum independent set problem. I will show an example in a minute. But there are also other types of problems, such as QUBO problems, that with little overhead in terms of qubit numbers can be encoded into our hardware. The third class of problems has to do with the so-called simulation or quantum simulation that is very well targeted to problems such as quantum chemistry or material design, but also to the solution of some fundamental problems in physics, such as the study of lattice gauge theories. Next slide, Yuval.
One thing I'd love for you to address is we earlier said that this is a dual mode computer. So what does dual mode mean, and why is it useful for some of these problems?
That's a great question, and this is a very emblematic feature of the meaning of dual mode. So the basic ingredients, let me start perhaps from a sort of pedagogical approach. The basic ingredients to perform a quantum computation are essentially the qubits, which are the fundamental tool in quantum computing, but also the gates, which are basically the operations that you can apply on top of those qubits. What you see on the left part of the slide, the digital gate-based modality, is essentially an approach of quantum computing where you start with a certain register that is initialized in the 0-0 state, and then you apply sequentially different layers of gates that can be either single qubits, 2-qubit gates, or even multi-qubit gates, if the technology or if the hardware is able to perform those. The second type of, and actually let me also emphasize that this digital gate mode is also universal. The second type of mode is called the analog quantum mode that you see here in the very thematic way on the right. It usually contains the same set of tools like the qubits, but now the gates are replaced by a global evolution, which is encoded into a quantity that in terms of quantum mechanics is called an Hamiltonian, that is usually time dependent, which means that it depends on the way in which macroscopically you perform the pulses on top of your qubits. And with these tools, in the analog mode, combined with the FPQA features that we have in our hardware, we are able to realize a nice simulations of square lattices. Perhaps you can just click and you see here a nice big square lattice, or Kagome lattices, which are also very important for quantum simulation of pieces of matter. But also you can really be very creative and create and design a map of the world, or even design several snapshots, take several snapshots of the hello world and create this nice video that you see here on the right part of the slide.
And Tommaso, is this just a animation, or is this something that's real from the actual computer?
These are actually snapshots, different snapshots that you take of atoms that are located within the so-called field of view, so basically the computational region of our machine. And then, of course, once you create and prepare these configurations, you can run the coherent evolution on top of those.
So how does controlling the qubit location help us in solving problems more effectively than perhaps today's gate-based computers?
Yes, I think this is a great question, also based on the nice input from Bob before, that was mentioning that actually users and perhaps also HPC centers are very interested and focused on real applications. What we see here on the left is essentially a map of potential locations of shops within the same chain in Lower Manhattan. And what you see here are basically a network of connections between these potential shops. Shops, of course, would like to have the maximum coverage in terms of clients, but of course, you don't want to put shops that share the same clients too close together, otherwise they will start competing. So practically, how do we solve this type of problem, this type of optimization problem with our machine? So we first replicate the topology of this network by locating precisely or designing an array of atom positions in our machine. What you see here is just a screenshot, is just a snapshot of locations, of course, not on scale. These locations are, of course, much closer in space on the order of few microns compared to several miles between different shops in Manhattan. And then on top of this snapshot, on top of this atom array, we design different types of dynamical evolutions in order to eventually take measurements of this atom array and define the optimal locations of our shop locations. That is actually an answer to the original problem that we see on the left.
So basically, we encoded the distance constraints through the physics. So we don't have to write code. It's the geometry that helps us do that. And I think that our applications team has shown that many problems that do not perhaps initially appear to have the ability to encode some of the constraints geometrically can actually benefit from that. But a question came up on the Q&A, and an obvious one. So, okay, I can decide where the qubits are, but how do I test this? How do I generate the excitation? How do I test different profiles?
That's a great question, Yuval. It has to do, of course, with fundamental AMO physics. AMO means atomic, molecular, and optical physics. We don't have the time here to go into such details, but again, feel free to reach out to us if you would like to have a more closer look on those physics questions. There is actually also a very nice way, if you want to sort of approach this problem at a sort of higher level, through our emulation tool, which is called Blockade. Yuval, you mentioned it at the very beginning of our presentation. Blockade is a high-performance testbed for neutral atom algorithms. It's powerful and flexible because it builds up on the natural capabilities of our Aquila machine. It is also very efficient because it has features that are really designed and developed for integration with HPC centers. And it also allows to basically work as an SDK, which means that you can initially design your job on Blockade and then launch and run them on AWS, on Amazon Braket. And if you go to the next slide, that we can present here a sort of very high-level number of features that our Blockade tool possess, which are related to the fact that it is also sort of written in Julia, which is a sort of very performant way of running certain numerical evolutions, numerical packages from the computational point of view. And then we designed also two specific features, which are multi-threading and GPU acceleration, that allows to speed up again by several times, so several X's, like Bob mentioned earlier, coherent dynamics that is actually reproducing what we could eventually obtain on the machine. Let me also mention that, of course, Blockade has certain limitations in terms of number of qubits or the effective dimension that of the physical problem that you can emulate. This is, of course, related to the fact that there are certain computational constraints to doing that. And of course, that's sort of the preliminary step before, again, running the same jobs on a true quantum simulator like our Aquila machine.
And so one thing that I wanted to ask, we've shown that we can solve several problems: optimization, machine learning, simulation, that there's a development environment that you could solve these both with us as well as partners. Amazon certainly has a quantum solutions lab and other systems integrator do it. But one thing that came on the Q&A that I wanted to ask you about, our system, Aquila, today takes about 10 kilowatts of energy. Is that important for an HPC center? Is that meaningful if they can solve a problem in Aquila that they're solving perhaps on a large-scale HPC computer? And even if they don't get a performance enhancement, does the energy saving matter?
Oh, you're leading the witness here. Because the question up there says how many HPC centers are interested in potential energy savings. The answer is simple: all of them. We're seeing a global interest in sustainability in its most altruistic sense, all the way down to these classical systems are just simply too expensive to run. And I use the Aurora system bound for Argonne National Labs shortly. That's a 60 megawatt system. That's a $300 million electric bill. I contrast that with when I was up at QuEra a couple of weeks ago, and they let me into the room with the Aquila system, and I ran around the back and I looked for power and cooling tubes and pipes, and I looked for electric connections. And there was nothing very interesting back there. And we had some questions about what are some of the environmental requirements. And it is clear that computationally, these systems can be 3 orders of magnitude less power consumptive to meet a specific computational requirement. 3 orders of magnitude. And when you pin people down and give them a beer or two and ask them about scaling, that scaling is pretty benign. So the idea of increasing qubit count doesn't have the same kind of trajectory that when you increase flop count on a classical system, which means that you can actually solve a problem. And this is where we get into some interesting aspects of quantum that I think are underexplored. Say I don't have better performance than a classical counterpart, but I can do it at 3 orders of magnitude less power. So now I take 5% of the workload off that Argon system, move it to a quantum system. I've just saved $15 million off the electric bill for that machine. That quantum system pays for itself in just savings in electricity. I haven't even talked about performance gains, and I'm only talking about 5% of a workload. So to me, as long as quantum computing can stay in that kilowatt range and stay 3 or 4 orders of magnitude below, the power to solution opportunities here are wholly unappreciated in my mind about the potential for this technology. And it's the scaling that excites me even more. And we talk about this idea of data centers just striving so hard for energy savings. We were talking to a client a couple of weeks ago, and we all agreed that PUE, which has been this energy utilization metric, is, well, he used a term I won't repeat here, but it's a fallacy. If I've got a PUE of 1.01, but I'm hooked up to a coal-fired electric plant out there, that's nowhere near as desirable as a PUE of 2 that's running off of renewable geothermal or solar or something completely benign. So what we need to do is really start thinking about data center design that actually address the issue of power consumption to solution. And quantum is probably one of the leading elements in addressing this issue. And I don't hear a lot of people talking about it. But I think you could talk about time to solution, but man, you get power to solution into that, you multiply those two things together, you've got a real cost saver here that I don't want to say it pays for itself, but it does. There's no other way to say it.
So let's assume someone was excited about the potential to solve problems or to explore quantum, was excited about the energy savings, maybe is getting questions from their customer base in the HPC center. Well, what are we going to do about quantum? A question that comes up, of course, is how can one work with QuEra? And we work in 3 different ways. One is solution development. So if you want to do a proof of concept, you've got an optimization or a machine learning problem or something else, either we can put you in touch either with our world-class experts internally or connect you with one of the partners that has done it. The second thing that we allow is premium access, which basically says you could access our system, run applications on it in sort of a pay-per-use type model. You could interact with our solutions experts to ask questions. We have office hours that help you figure out if a problem can be mapped efficiently into a quantum computer. And of course, we also lease machines. So if you want your own machine, then we can work with you to achieve that. I did want to ask both of you, perhaps Tommaso, you first, and then Bob. So if I'm an HPC center manager, I want to bring in quantum, what do I need to do from a workforce training perspective? How do I get the buy-in in my organization? What kind of people or expertise do I need in my HPC center for this integration to be effective?
Great question, Yuval. I think that here among the attendees, we have several users as well as managers of different HPC centers. And what I think that we hear from an interaction with all these people is that quantum computing has a relatively steep learning curve, which means that it takes time first to learn what quantum computing is at a very basic level. And second, the other important thing is that if you want to integrate this technology with your current existing CPUs or GPUs or clusters in general, you need to sort of validate the technology. So validation has to come from people that have at least a basic knowledge, a basic understanding of this technology. So if you combine these 2 factors, so it takes time to understand the technology, it takes time to validate the technology, I think that you should start sooner rather than later. and start thinking about creating even a smaller quantum team within an HPC center to interact in a proactive way with companies like QuEra to understand what is the best path to work together and exploiting all the benefits of quantum computing.
And Bob, let me actually change the question a little bit when I ask you. You mentioned the big three: optimization, simulation, machine learning, related to AI. People can look at quantum and say, well, ChatGPT is doing quite well. And I'm not sure that today you can do much better or even close to ChatGPT with a quantum computer. So why is there an interest in AI and machine learning with quantum computers for HPC centers?
Well, the first thing, and if you want to talk about ChatGPT, I've been introduced to a new concept looking at large language models, which is petaflop days, which is I've got a machine that has X number of petaflop capabilities, and it may take 15 days to train it. ChatGPT, some estimates are it costs $100 million of compute capability to train that system. That's beyond the reach of most organizations to do that kind of stuff. So, and the HPC, the large language model world is moving beyond. We're seeing new large language models that are crazy big, crazy demanding, and completely out of the realm of what's going on. I saw an estimate that said a certain training model that went on the Fugaku system, a $1.1 billion exascale system in Japan, would take the next ChatGPT-4 would take 9 years of training time on that system. So people are looking at that world is on a fascinating and ultimately really frustrating trajectory. If quantum computing can step in and do the kind of performance acceleration, or perhaps provide some interesting shortcuts or some interesting algorithms that don't require massive training sets. And by the way, if you trust ChatGPT, remember a large part of its data set comes from Reddit. Okay, that should keep everybody up at night. So quantum computing can offer an alternate scenario to some of the technical requirements and some of the data demands, and certainly the growth in compute requirements that we're seeing in some of these generative AI applications. So again, it's the same story that we see in the science and engineering mod sim world. In the AI world, there's an opportunity here for a much lower cost, more effective compute capability than what we see in the classical world.
And when you look at quantum computers in production environments, I mean, first, do you see them as running standalone, or do you see more of hybrid classical quantum algorithms? Do you see them running real-time operations or more in batch mode, periodic calculations? Where would you expect quantum computers to show up in a production environment?
I mean, I would expect them to show up like we see all other typical HPC environments. There's going to be a percentage of what we would call HPC research facilities, and an organization like Lawrence Berkeley National Lab would be an example. They have 6,000 users running 600 different kinds of research jobs. So it's short programs, a real variety of programs. You can contrast that with, say, a production environment where, say, an automotive or an aerospace manufacturer wants to run a simulation that may take a week. We know of oil and gas companies that run one job for 3 or 4 months. So there's those kind of R&D and production environments. But the third leg here in quantum, which I find interesting, is the near real-time applications. And here it's, okay, I'm Frankfurt. If you've ever flown into Frankfurt, the gating assignment is absolutely bedlam. If one could come up with a real-time quantum computing application that could every 15 minutes come up with an optimal gate scheduling program in a way that is classically intractable on a classical system, because you've got a 15-minute deadline, because every 15 minutes something changes. You can't pre-compute certain things. So I see quantum in the near term, because of the NISQ era and the qubit limitations and such, as having a niche advantage right now, what I would call near real-time computation. The idea that I could come up with an optimal solution for gate arrival scheduled to Frankfurt on a classical system, but it would be 3 days out of whack. If I could do it on a quantum system, a little more heuristics, a little better optimization, and do it every 15 minutes, it's not a pure production level environment. It's more of a near real-time integration application. And that I see as a very compelling niche for quantum in the next few years. This kind of third leg of HPC-ness that we don't see in the classical world. No one has a high performance computer doing scheduling at Frankfurt. They may have something that works. I don't think it works very well, but there's probably lots of optimization. Delivering FedEx, one of your FedEx trucks breaks down. How do you rejigger in real time to optimize the other 1,000 trucks in your network? Classically intractable in real time, not on the quantum system.
So real time here is not real time as in I'm passing 100 million credit card transactions a second and I want to detect fraud, but real time, every few minutes, maybe I want to balance the portfolio every, you say 15 minutes based on market changes.
Now, exactly. Yep.
Now, Tommaso, what are you seeing with regards to, so HPC Center gets excited about using a quantum computer. What's the best way to go about it? Is it remote access used through someone else's cloud? Is it co-location, put some classical resources in Boston next to our quantum computer or another location? Or is it just an on-premises computer? And maybe, Tommaso, you can go first and then Bob, for your perspective.
Yes, I think the great question again, Yuval. I think that perhaps Bob already presented a little bit in terms of an analytic perspective on how users, how HPC centers see the different type of modalities. Each one, of course, has pros and cons. Remote access is the best way perhaps to start. It's usually available as soon as the quantum computer is connected either to AWS or directly with the company's cloud service. We offer both at QuEra. So again, we believe internally that this is the best way to start working with us. Co-location, again, means essentially that you can attach the HPC part of this integration into the quantum computer. And so perhaps if we have an HPC or a cluster that is really related or close to our QuEra computers, that would also be absolutely very easy to implement, but also helpful in terms of service, because of course maintaining a quantum computer is expensive, not only from the point of view of the pieces and that you need to buy and replace, but also in terms of workforce, as we were mentioning before. Then the third option, the on-premise, is certainly very valuable for those HPC centers that need to work out all the details, that need to have complete control on the full HPC side, as well as the cluster, as well as on the quantum computer. And here it is actually very important to keep into account that, for example, we are still at an early stage, and there is actually the need to develop also the full software stack around that connects the QPU, the quantum processing unit, with the classical hardware. And in this respect, I think that HPC centers have a great responsibility and will be of great help actually to develop all these pieces and put them together.
And Bob, well, how do you think about this? And by the way, why would someone want an on-premise quantum computer, given that they change so quickly that if you buy a quantum computer today, maybe in 5 years it's obsolete? Why would someone want? You said 70% go through the cloud. That means 30% wanted some fashion of on-prem. How do you think about that?
Well, there's always going to be on-prem. Whether you have proprietary data that you want to protect, you don't want it flying through the air to a CSP that you may not completely trust. You may have government requirements, regulatory issues, national security issues where stuff can't leave, the building behind the big tall fence. You may reach a point where you're starting to pin access to that quantum system, and it just becomes fundamentally cheaper to have something on-prem. Cloud service providers, they have a profit margin, so they're adding incremental cost access to that system. And if you're hitting that system 24/7, all day, every day, someone's going to do the math and say, we look at it in the HPC world and know that there are crossover points. If you have this much utilization of your HPC, bring it back from the cloud and go on-prem. It's going to be cheaper. The remote access thing is magnificent for exploring different kinds of modalities. The cost to barriers to entry, to kick the tires on someone else's modality, those things are great on cloud access. So to me, it's just a wealth of opportunities here, and you can come up with any scenario that works best, or you can come up with all scenarios that work best. Free to explore those things and really just decide, what do you need to do? I expect to see on-prem become more prevalent over time, simply because of usage requirements, whether it be proprietary, regulatory, or just utilization rates going up. Now, that doesn't mean you go out and you plunk down X million dollars on today's quantum system. You're going to be thinking about leasing. You're going to be thinking about incremental upgrades. You're going to be thinking about end-of-life requirements as well. How do we do this? So it's not just, you just don't go kick the tires, write the check, and they back it off. Because while this integration method is important, the thing that matters most at this point is how you can engage with the experts who supply this technology. You don't back a truck up, drop your quantum system off, and then speed off into the night. It's really about service. It's about expertise. It's about customization. And we already heard about integration being the single greatest determinant of vendor capability. So regardless of options, and I would argue the wealth of options is the best way to go right now. Offer any access point, but the key determinant is how much handholding, how much expertise, how much support any of these options offer to you. And I would rate that parameter, at 0.8 when it comes to the equation in terms of who do we go with. It's really about the support and expertise, applications, understanding verticals. You may have the best on-premise system in the world, but if you can't talk to the guy that supplied it, it's a hunk of metal in your basement. And so that's really what matters here.
These are great points, and I wanted to add a little bit of perspective. Two things. One, these can usually coexist. So for instance, remote access could be an on-ramp. You could say, okay, I'm trying it on a limited basis. I'm going to use 100 hours, 200 hours of machine time, and then see if I get the value that I'm expecting and make the ROI calculation. And then conversely, if you order a machine from us, we don't have them in stock for next day delivery. When I say we have it on Amazon, I don't mean we have it on Amazon.com. We have it on Amazon bracket, right? And so while you wait for the machine to be manufactured, delivered, installed, and so on, you could use remote access to get everyone excited, educated, and starting to use the system. The second point is actually about capacity and control over the system. So if you are running your 15-minute Frankfurt gate optimization, you want to be able to run this task every 15 minutes and not submit it to a cloud provider and hope that there are not enough jobs, that there are not many jobs ahead of you, that you get the results in 2 hours. So at some point it becomes mission critical to assume that you can control who's using, when are they using, what are their priorities, and so on. We're getting close to the end of the webinar. I wanted to add a couple of things before we close. First, there's a question I see on the Q&A. Are we going to use hyperfine qubits, qubits, and so on and so on? I had the pleasure of giving a presentation at Q2B Paris last week. I think the video will be up in a few weeks, and we give a more detailed look into the future of QuEra, how we go to 1,000 qubits, what are we going to do about error correction, what are we going to do about digital mode, and so on. So that's something that stay tuned for, or ask us after the webinar. Of course, we are standing by to help you explore how QuEra can help with your HPC environment, so feel free to contact us. But before we close, Tommaso, Bob, any last thoughts, anything that you say, hey, if you remember one thing from this webinar, this is what I'd recommend that you remember? Perhaps, Bob, you go first.
Oh my gosh, thank you for that. That's surprise. The key here is exploration. It's not here today. It's not going to solve all your problems, but the time to start is now. My favorite quote of this week is from Vince Lombardi, which is, if you're 5 minutes early, you're 10 minutes late. And I think that's the case. You got to start looking at your use cases. You have to start examining your existing and projected code base to say, where are most vexing problems and how can quantum help that? And that's the first necessary step towards trying to really build a case towards why you need to bring quantum into your compute environment.
And I can double down on Bob's words, so we can you serve me an assist, because we have two amazing products that you can start playing essentially today. Blockade, our emulation tool, and Aquila, again, remote access. You can connect to Aquila through AWS. And if you have other questions, please feel free to reach out to us at info@QuEra.com. Thank you, Yuval, and thank you, Bob, again.
Thank you.
Thank you, guys, and thanks to all that participated in today's webinar. And we look forward to welcome you in a couple of weeks for our next webinar. Stay tuned and have a wonderful day.
Thank you. So long now.
Thank you. Bye-bye.